All right, to conclude the session, we're going to have a paper by the Aptos team on their prefix consensus, and Zhuolun will be giving the talk. So.
Thank you. So, good morning. This is Andrei Xiang from Aptos Labs. Today I'm going to talk about prefix consensus and how you can use it to construct censorship-resistant BFT protocols. And this is joint work with Andrei and Sasha from Aptos. So, most blockchains today, it doesn't give you inclusion guarantee. So basically, there's a leader that decides what transaction can go into the block. So this is pretty bad for DeFi and trading, and we want to improve that. So to start with, I want to give you our model assumptions so that we are on the same page. So we consider the standard BFT setting where you have 3F+1 nodes, F of them is Byzantine, and they all have signatures and PKI setup. Yeah, like I said, we assume the BFT setting, so there is no incentives involved. And for the timing assumption, for some of our results, we only assume asynchrony. For some of the blockchain protocols, we'll need partial synchrony. And we consider a multi-slot consensus problem where in each slot, every validator can submit their proposal, and the consensus need to decide one block for that slot. And our definition of censorship resistance is also defined per slot. So here, a slot will be censored if it excludes an honest proposal. So here is a simple example here. So the block on the top is not censored because it includes all the honest proposals, and the block on the bottom is censored. So by our definition, if the slot gets skipped or it somehow produces empty block, then we consider that slot censored as well. So this is a bit different from previous works. And what our protocol guarantees is F censorship resistance, meaning there can be at most F censored slots, including those empty slots. And of course, this is after GST, where the network is synchronous. Okay, so before I give you our results, I want to briefly mention our ideas in the high level. So in our protocol, each slot, our protocol will commit a prefix of the proposal vector. And the vector is ordered according to some ranking among all the validators. Like here, in a good case, you have 4 proposals, each from different parties. And in the good case, they all get included. But we know that there are some malicious nodes that try to do censorship. So here, like in this example, the second party is bad. In our protocol, it can only censor by trying to cut at its own position in the vector. So the second party is bad. It can censor all the blocks after it, but not the block before it. So these are proposals within one slot, just to be clear. These are not different blocks across slot. So what we do with this is once a malicious party that censors, it also reveals itself. So in the next slot, we will demote that malicious party to the end of the ranking. So here, the party is ticked to the end. So even if it wants to censor again, it can only censor itself. So all the honest proposals will be included in this case. So here is only a very high-level idea. I will talk about how we implement this mechanism in the following slides. Okay. So now, as for the results, we have a stack of protocols building on top of each other, starting with a new primitive we call prefix consensus, which is deterministically solvable in asynchrony. So which means it's strictly weaker than consensus. We show it has 3 round tight bounds. So building on top of it, we build strong prefix consensus, which add agreement to the prefix consensus. So it is as strong as consensus. And we have a leaderless construction under partial synchrony. So the leaderless means the protocol will terminate even if the adversary can suspend one party for every round. So by definition, the leader-based protocols are not leaderless because the adversary can just always suspend the leader, right? So then the leaderless protocol will not make progress. Then finally, building on top of it, we have a multi-slot BFT SMR, which is another name for blockchain protocol, which is leaderless. It has multi-proposer. It achieves F censorship resistant, so meaning there can be at most F censored slots. And it has an amortized 4-round commit latency. All right. So first, let me talk about what's prefix consensus. So this is a new primitive where each party, it has an input vector. So you can think the vector as the proposals you receive from all other parties in that slot, ordered by some ranking. Okay. And the primitive need to output a pair of vectors called low vector and high vector. And it needs to satisfy some properties. The first is a prefix property where all the low vector of any honest party need to be a prefix of any high vector of any honest party. The second is validity, saying any honest low values need to extend the maximum common prefix of any honest input. And then we have standard termination. So here is a simple example. You have two honest inputs. They differ at the last elements. So their maximum common prefix is A, B, and C. And you have low values extending that, and you have a high value extending the low value. So if you think about what this primitive means a little bit, you will see that the low value we define is something that is safe to commit right now. And the high value we define is like something that is safe to extend in the future views, right? And note that there is no agreement. So here, honest party, they can have different low vectors and high vectors. So that allows us to solve it deterministically under asynchrony. Okay, so we have a pretty straightforward 3-round protocol. And I think I am not going to the details here, but the protocol is pretty straightforward. It has 3 rounds. So every round, you basically first sign on some vector. You send it to everyone. Then you collect the signed vector from all others, from a quorum of parties. Then you compute some new vector based on the quorum that you collected. And then you send, and then you sign and send the new vector again in the next round. So you do this for 3 rounds. And in the end, you can find this protocol satisfy all the properties we need. So also, there is only all-to-all communication, so it's a quadratic number of messages. And we have a communication optimized version in the paper as well. And our construction, in addition, has 2 more properties. One is verifiability, saying that the low and high outputs you get, you can also get some proof to show that these values are valid. So any verifiable outputs, they will satisfy these properties of our protocol. So this is important when we construct the other protocol using this primitive. So the outer protocol can verify the outputs of the prefix consensus. So the second property is called accountability, which relates to the main idea I just talked about. So basically, when you have an output that is not full length, if the output is truncated at some party, let's say B3 in this case, we can decide that the party 3 is malicious, right? So using this property, we can, like, you can roughly see how I can use the previous idea to demote the parties in the blockchain protocols. Right, and we also have some lower bound results, saying 3 rounds is necessary to solve prefix consensus under like this number of faults. So again, I'm not going into the proof details, but it uses standard indistinguishability arguments, and the proofs are in the paper. So next, I'm going to talk about strong prefix consensus building on top of prefix consensus. So it basically adds one additional property called agreement, requiring all the high values, high vector outputs to be the same among all the honest parties. So with that, it is as strong as a standard consensus. So as a warm-up, there's actually a very simple and straightforward way to construct a strong prefix consensus protocol using prefix consensus and any validated consensus protocol, such as any leader-based BFT protocol. So basically what you do here is first you run the prefix consensus. It will output a low and high output. The low output you can immediately output for the strong prefix consensus, but the high outputs, they are different across the honest parties, so you need to use the validated consensus to reach agreement on it. Right? Once validated consensus reach agreement on the high value, you can output that high value as the output for the strong prefix consensus. So this is pretty straightforward and probably works well in practice. But the thing here is using a leader-based BFT protocol bring back the leader. So it's no longer leaderless. And if we want to use a leaderless validated consensus black box, it's pretty expensive. So that's why we decide to construct the leaderless protocol directly from our prefix consensus. So now I will give you the brief idea on how we construct the protocol. Basically, it runs in multiple views, and each view you will run a prefix consensus instance. And like in before, the view 1 will run prefix consensus. You output low values immediately. And the high values, you need to somehow agree on it in the following views. So in the following views, you run prefix consensus, but not on the real output like blocks. Instead, you run its own vectors of certificates. So where the vectors of certificates, each element is the certificates of some party for the previous view. So basically, you run this over and over, and eventually when you commit on some view with some non-empty vector, then you look at the first non-empty certificate in the vector, which were linked to a previous parent view. And in that parent view, you also commit a non-empty vector, which is first non-empty certificates again linked to a previous view. So you do this recursively, and eventually you will reach at the first view. And we can show that for the other honest parties, they will have agreements on the same high vector for the first view. And also, this primitive is accountable if we use an accountable prefix consensus for the first view. Okay, so finally, based on the strong prefix consensus primitive, we can build a blockchain protocol. So now the construction is pretty straightforward. We have a few steps. First, all the parties will broadcast their signed proposals. Then they will collect their proposals and rank them into a vector. according to some ranking. They then input this vector into the accountable strong prefix consensus, which gives you low and high output. So the low output, it may produce very quickly, so you can already commit those proposals. For the high vectors, the strong prefix is guaranteed that all the high vectors are the same. So these basically finalize the commit for the slot, and you can start the next slot once you finish it. And why this protocol is censorship resistant is because of the way we update the ranking. Like I said very early in the talk, we will demote a malicious party to the end of the ranking. So here, like in this example, we have a party that tried to cut the outputs and censor all the blocks, all the proposals after it. Then our accountable strong prefix consensus will catch this malicious party, right? Then in the next slot, the ranking rule will just move the malicious party to the end of the ranking so that it can no longer censor any honest party. So since each malicious party can only censor one slot before it's moving to the end and no longer can censor anyone, we will have at most F censored slots because they are just F malicious parties. And if we look at the latency, it's in the happy path is 4 rounds, which includes 1 round for all the parties to exchange their proposals for the slots, and 3 rounds for you to run the prefix consensus and produce the low value. So in the happy case, the low value includes all the honest proposals. But there is some subtlety on why I only claim amortized 4 round latency, because a malicious node could make the honest proposal to be not included in the low value, but included in the high value without censoring the honest proposal. So you can do that without being caught and demote. So our protocol also deal with this by looking at any truncated low value. So this truncated low value will also blame such malicious party and make it demoted. Then once everything is good in the amortized sense, we have a latency of 4 rounds just like this. So in addition to the main results I talk about, we have some bonus results that can be derived from our protocols. The first is we build a reduction between our prefix consensus and the graded consensus. And we show that the type 3 round bound also apply to graded consensus. And the second one is our leaderless strong prefix consensus can be directly used to solve leaderless binary consensus, which gives us improved protocol on top of previous work. The third one is we can make a prefix consensus 2 rounds under higher resilience. So this is very similar to standard consensus as well. So when you have a higher resilience, you can do 2 rounds. So finally, before I conclude, I want to draw a quick comparison with previous works on censorship-resistant protocols. So here in the table, the first work by Abraham et al. Is a paper that Lin just talked about. And so they have a censorship definition that's require you either to commit all the honest proposals in the slot, or you can skip the slot entirely. And they have a tight bound on the latency, which is 5 rounds. And the second paper, MCP, have the same censorship resistance, and both protocols are leader-based. So in comparison, in our work, we count skipped slots as censored as well, and we allow up to F censored slots. So in some sense, these two definitions are incomparable. Like it's not one stronger than the other, or vice versa. And we think in a long-running application like blockchain, like F censored slot is really negligible because every second you can produce multiple slots already. And also our protocol is leaderless, so there is no single leader that you can try to DDoS and slow the protocol down. And for commit latency, we have 4 rounds, which somehow break the previous lower bound, but it's because we consider the amortized latency, and our censorship definition is a bit different. Okay, so finally to conclude, we propose a minimum primitive called the prefix consensus, which we think is useful for reasoning about inclusion. It's asynchronous, deterministic, and has a tight 3-round bound. And we use it to construct a leaderless multi-proposal blockchain protocol, which allows only up to F censored rounds. And it has amortized 4 rounds commit latency. The key idea here is we always only demote the malicious parties to the end of the ranking instead of just banning them. And yeah, with that, I'm happy to take any questions. Thank you.
Questions for the speaker? Maybe one quick question. So what would go wrong if you did ban instead of demote?
Yeah, if you ban a party permanently, it may be honest, but it's under asynchrony, right? So you may ban it forever, even though it's an honest party. So basically, you cannot distinguish honest but slow with malicious parties in partial synchrony. So you cannot just ban a party forever. Right.
Got it. Any questions for the speaker? All right, let's thank all the speakers of the session one more time.